Good afternoon, students. Am I audible? Okay. Are you getting the screen there? Okay, fine. Okay, so we were the topic of different types of line codes. In the last lecture, we have studied different types of line code in time domain analysis. Okay, so here is the comparison of this different line codes. So these are the parameters, or we can say the properties. Okay, or advantages or disadvantages. So in the first column, there are the parameters. The first one is the transmission of DC component. Okay, so always remember while transmitting the DC digital signal, okay, binary form. So there should not be any DC component present. Okay, so if you consider the polar RZ signal, so in that case the DC component sometimes present. In polar NRZ also it is present. Whereas in bipolar NRZ and Manchester, there is no DC component. Means particularly the format that you are using for bipolar NRZ and split phase Manchester. So that is the advantage of this AMI and Manchester pattern here. Okay. After that, obviously signaling rate would be same. Whatever the data is we are using for a different format, but signaling rate it is same. Okay. Noise immunity in polar RZ it is low. For polar NRZ it is low. For bipolar AMI it is high, and for split phase Manchester it is high. Now synchronization capability, that is very important parameter. So in polar RZ and polar NRZ it is poor as compared to AMI and Manchester. It is very good in that particular AMI and Manchester. Okay, the bandwidth required, so it's very simple. When the signal is RZ signal, so bandwidth get double. When it is an RZ, so it remains constant. Okay, but it is RZ and it is get double there. The crosstalk is high in polar RZ, polar NRZ, and whereas in AMI and Manchester it is low. So this is a simple, brief comparison that different types of line codes that we have studied in the last case. Fine. Now these are some examples, the practical examples where we are using that is serial communication RS-32 signaling. Okay. So you can see. So here you can see here. Yeah. So this is the overall bit pattern. It is one is here, it is 0, here it is 0, it is 1, 0, 1, 0, 0, 1, 0, 1, 1, 1. Okay. Now this is the data that we have to transmit by using RS-232 signaling. RS-232 signaling. This is one of the format. Okay. But here you can see the first bit there is 1, second bit it is 0. So this 1 and 0 we represent for the synchronization here. For the synchronization, actual information bits are we are getting from this point, means from third bit to up to this point. So these bits are representing here information. Okay, and the last 3 bits again here representing the redundant bits here. Okay, so parity bit is there, stop bit is there, and clear is there. Okay, so this type of synchronization or the addition of the redundant bits or bit stuffing is the particular word that I can say here. So the bit stuffing that we are using to correct the bit error. Okay, after that to maintain the synchronization between the frames. Okay, so along with the information bit we are adding some extra bits. So these are the extra bits at the start of the sequence of information and at the end of that particular information. Okay, now this is the overall bit pattern and this is the representation. Okay, so for you can see here for bit 0 you can see here the positive level is there. Okay, and for bit 1 is here negative level is there. So one of the pattern we have studied is polar NRZ. So polar NRZ, in that case we represent the plus voltage for bit 1 and negative voltage for bit 0. Okay, but here it is inverse. For bit 0 we are using the positive voltage and for bit 1 we are using the negative voltage. So this is not a polar RZ, it is a differential polar RZ. It is a differential differential polar RZ. Okay, that is a differential polar RZ. So there are different types, but the basic types already we have studied. So this is one of the type of serial communication of RS-232. Similarly, USB signaling is there. Already we familiar with the USB. Okay, so this is the raw data, means for a synchronization of the frame, means packet. So this is the representation is there, the bit stuffing. Okay, to start to identify where or actually the frame is starting and where actually the frame is ending. Okay, so for that purpose we have to do some bit stuffing, or generally called as the bit padding is there. Okay, and this is the NRZ data. So this is the encoded data that we are using one of the type of line code format. This type of signaling generally we use in USB case. Okay, that is called the bit stuffing. So this is all about the practical applications that we use the different line codes. Okay, different formats. So already just go through the different types of line codes. Okay, now this is all about in time domain. Now let's understand the power spectral density. The power spectral density of the this different line codes. Okay, now here what is meant by exactly the power spectral density here? Okay, now a function which gives the distribution of power of a signal at various frequencies in a frequency domain. Okay, I'm repeating again. What is the power spectral density is? Power spectral density means a function which gives a distribution of power of a signal at various frequencies in frequency domain. Okay, so with the help of some mathematical analysis we will understand what is the exactly meaning of this power spectral density. Okay, now here the output distortion of the communication channel depends on the power spectral density of the input signal. Okay, what is the meaning here? Power spectral density of line codes means the output distortion of a communication channel. Okay, it is depends on the power spectral density of the input signal. Okay, so therefore the power spectral density depends on the pulse rate, pulse shape and pulse distribution. These are the very important points that you have to understand. Okay, the PSD, power spectral density, it depends on pulse rate, pulse shape and pulse distribution. Okay, now pulse rate means what? The spectrum wides with the pulse rate. Okay, pulse shape means what? The smoother pulses have narrow power spectral density. Okay, now the distortion can result in, means the overall shape of the signal here, means output pulses are not longer than the input pulses. As you can see from the transmitter side, this is the information signal that we have. Let us consider here it is 1 0 1 1. Okay, but due to distortion, means which distortion? The inter-symbol interference. We will discuss later this one, inter-symbol interference. Okay, so what will happen due to that inter-symbol interference? This is called as the inter-symbol interference. Okay, so due to distortion, the shape of this signal, means this is nothing but the TB. This is nothing but what? TB. Okay, but here actually this is TB. This is TB. Okay, but some part of this pulse, means the duration of this bit 1 is overlapping with the duration of the 0 pulse. Okay, you can see here. So that is called as the inter-symbol interference. Okay, so if such inter-symbol interference is there, so that is the meaning here. The output distortion of the communication channel depends on the power spectral density of the input signal, means the pulse rate, pulse shape and pulse distribution. Okay, that is the overall example. So the distortion can result in, means the shape of the particular signal. Okay, now let's understand with the help of one of the bit pattern here. Let us consider here the PSD is nothing but what? Is the Fourier transform of the autocorrelation function. Okay, PSD means power spectral density. PSD means the power spectral density is the Fourier transform of the autocorrelation function. So autocorrelation function means what? The first word is auto and second word is what? Relation. Okay, so when the parameter which are related with the common signal, I'm repeating, when the parameters are means related with the common signal. Okay, so which parameters here? Mean. First parameter is mean and second is the time difference. Okay, mean of that particular signal and time difference of that signal. Okay, so here the autocorrelation function, in this case this parameter are related with the common signal, the same signal. Okay, that is called as the relation between of the same signal, relation relation of the parameter of the same signals. That is called as the autocorrelation. That is called as the autocorrelation function. Okay, so here the power spectral density is nothing but what? The Fourier transform of the autocorrelation function. So this particular topic we will study in detail in unit number 3. In unit number 3, we have to study this parameter in detail, autocorrelation function. Okay. Now let us consider the rectangular pulse and its spectrum. Okay. So this is the rectangular pulse. First, one of the pulse we can consider. For example, if you have a signal like this, it is 1, 0, 1 like this. So this first pulse we are considering. Okay. First pulse we are considering here. Okay. We know the overall duration it is TB. Overall duration it is TB. But we are mentioning this power spectral density at the center of the bit. At the center of the bit, you can see here, this is the power spectral density at the center of the bit. So overall duration here it is TB by 2, and here it is minus TB by 2, minus TB by 2. So we have to integrate this part, minus TB by 2 to plus TB by 2. Minus TB by 2 plus TB by 2, and we have to check what is the exactly power spectral density that we are getting in this duration, minus TB by 2 to plus TB by 2. So it is 1, means when the time is 1, this 1 when is less than or equal to T by 2, otherwise it is 0, otherwise it is 0. So therefore, if you're taking the Fourier transform, okay, means the Fourier transform is what? The rectangular pulse Fourier transform. So obviously we will get here the sinc function. What we are getting here, sinc function. We can see this type of sinc function we are getting. Okay, so here you can see here in the first lobe itself we are getting the maximum power. The first lobe itself we are getting the maximum power. Okay, now let us understand with the help of some mathematical analysis. Okay, now power spectral density of the line code. So here the PSD of the line code depends on the shape, as already I told that the shape of the pulse that correspond to digital value, Okay, now consider the PAM signal, pulse amplitude modulated. So it is a distorted signal. It is a distorted signal. Okay, only one pulse is there, and there are different types of pulse. The train of pulse. It is a train of pulse. Okay, so if you write the mathematical equation for this particular signal, okay, so it is nothing but what? Y of t is equal to summation. Summation means summation of this pulse, summation of this pulse, this pulse, up to whatever the signal is there. Okay, so this k is equal to minus infinity to infinity, and these are the parameters that we have to consider. Means the overall time duration. Okay, it is TB is there, after that 2 TB is there. Okay, after that 3 TB is there. Okay, so that is the overall duration with respect to that power spectral density. Okay, where TB is a pulse period. Okay, the pulse may be wider than TB or less than that TB. So already we know it TB plus delta, and what happens TB minus delta. TB minus delta. So it is early synchronization, it is late synchronization is there. Okay, so the overall the weighted value, if you want to calculate it for this particular signal. So this is the mathematical equation of this signal. Y of t is equal to summation of minus infinity to plus infinity for the shape of this particular signal Y of t. Okay, so it is k plus 1 TB, it is k TB, k plus 1 TB, 2, 3 TB, like that. Overall, we will get the value. Okay, now, yeah. Now let's understand with the help of one of the signaling pattern that we have, or data format. So it is a power PSD of polar signaling. PSD of polar signaling. So already know polar means two polarity, positive and negative. So bit 1 we represent like this. So it is RZ signal. So it is like this, and if it is bit 0, then we represent like this. Okay, return to 0. Polar RZ means return to 0. So it is bit 1. Here it is bit 1. Okay, it is 1 1 1. After that it is 0 0, like this. Half part return to 0. Okay, so here you can see 1 we represented plus sign, and 0 we represent the minus sign. Okay, it is plus sign, and here it is minus sign. So with respect to this the pattern of the power spectral density, means the pattern of the polar RZ. I'm writing here, it is polar RZ. Okay, so what is the assumption we have to make? We have to consider time T is equal to center of the bit here as per this calculation. So what we will do, this is the pattern that we have for bit 1. Okay, this is the pattern we will have. So what we will do, we will consider time here T is equal to 0. Okay, so what we will have, it is minus TB by 2, here it is 0. We will put time is equal to 0 at the center of the bit, and here it is plus TB by 2. Plus TB by 2. Okay, so as per this calculation, so what will have two integration, because minus TB by 2 to 0 we will have some voltage level, and from 0 to plus TB by 2 we have a zero level is here positive level is here and 0 level is here. But if you consider the bit 0 here, what will have positive level here and negative level here for the rest of the duration 0 to TB by 2. Okay, so if you are considering bit 1, so we have a positive level. If you are considering the bit 0, so we have a negative level initially. So whatever the voltage level here, we will consider plus or minus sign, plus or minus sign. So if you are solving this particular integration, two integrations are there, minus TB by 2 to 0 plus 0 to TB by 2. Okay, so after solving these two integrations, so such type of signaling we will get here. This is the mathematical equation is given. So the overall power spectral density we will get like this. The overall formula, if you calculate here, we will get like this. Okay, so power spectral density, this is the notation of power spectral density, S of F. Just remember the power spectral density notation is S of F. Okay, is equal to the Fourier transform of the pulse. P of F means what? The Fourier transform of the pulse square divided by TB. Okay, Fourier transform of the pulse, I'm talking about the single pulse, square divided by TB. So after calculation of pulse, whatever the Fourier transform we will get after solving this integration, that value we have to put over here. So this is the generalized equation. S of F is equal to P of F whole square divided by TB. Okay, so here for polar signaling, P of T, P of F. So P of F we will get like this: TB sinc function pi TB F. TB sinc function pi TB F. Okay, so PF square is equal to TB square sinc square pi TB F. Okay, similarly here for RZ, PF is equal to 1 by 2 TB sinc function 1 by 2 pi TB F, and if you get this square, this is the format we will get. So if you plot the power spectral density of polar NRZ, so here we will get power spectral density of polar NRZ, S of F is equal to PF square whole square divided by TB. Okay, so PF square means what? This one, TB square, that is sinc square, this value divided by TB. Okay, so this TB and this TB will get cancelled, so only remaining term is TB sinc square of pi TBF. So this is the power spectral density of polar NRZ. Okay, so if you plot here, so such type of spectral density function we will get like this. Okay, such type of power spectral density we will get here. So yeah, this one, if you want to this is the actual signaling that I said. This is for a half bit pulse. This is for the half bit pulse, TB by 4 sinc square pi TB by 2 divided by 2. Okay, so if you are considering only the power spectral density of polar NRZ, so here we will get the 2. Here we will get the 2. It is RZ, so therefore we are getting here 4. Okay, so this is the pattern. Let me know, have you understood or not? Is it okay? Because it's the mathematical equation, the standard mathematical equation that we are using here. The standard mathematical equations here we are using here. Okay, so yeah, so what you have to understand here, initially we derived the common equation. Which common equation? The power spectral density. So what is that common equation? S of f is equal to mod of P of f whole square divided by TB. Okay. Now, this P of f is nothing but what? The Fourier transform of single pulse. So how do you calculate for polar RZ? I am repeating again. Polar RZ के लिए हम क्या करेंगे? Here at the center of the bit we will put t is equal to 0 value. So overall duration would be here TB by 2 minus TB by 2 0 plus TB by 2. Okay, and we will solve this two integration minus TB by 2 to 0 plus 0 to TB by 2. Okay, and we will have this the function here. Which function? The spectral function here. Okay, so after solving this one we will get here sinc function. Which function we will get? Sinc function. As you can see here, yeah, this type of function we will get. This after solving that integration, this function we will get here. Okay, and after that we have to take the square of that particular Fourier transform of that pulse, right? So the after that in this common format, S of f is equal to P of f whole square divided by TB. Divided by TB. So here we have to put this value. Okay, so graphically we can represent like this. Graphically we are representing like this. Okay, for further detail you can refer this book, Lati and Ding book, figure number 7.6, page number 387. Okay, that is the author name. Okay, it's page number. Online you will get the PDF copy here. So this is the power spectral density function PSD of polar NRZ signal. Similarly, this is the pattern. Okay, for polar NRZ. After that, for polar RZ, because it is returned to 0, so the main lobe will starting from 0. So that is the power spectral density of polar RZ. After that, for a split phase Manchester, we know for bit 1 we are representing like this, positive end with negative, and for bit 0 we are representing start with negative end with positive. Okay, so for this type of pulses we will get such type of power spectral density for split phase Manchester. For bipolar NRZ means AMI, for AMI we are getting such type of power spectral density. Okay, so this is all about the power spectral density. Just remember how to draw. So for polar NRZ, for polar RZs, okay, so just wait, I'm drawing here. Yeah, for polar as well as unipolar NRZ. Okay, for polar and unipolar NRZ, the pattern power spectral density function we will get like this. Okay, so for unipolar NRZ, this value, such type of pattern we will get, but for polar NRZ, the pattern we will get like this. Okay, so this power we will get maximum in unipolar NRZ, whereas in polar NRZ the power would be less. Pattern would be same like this. Okay, but the power level here on the y-axis there is the power, and on the x-axis there is a frequency. Okay, so in unipolar the power level is high, density is high. Okay, whereas in polar NRZ density is low. Okay, so if it is RZ, okay, so unipolar RZ, so pattern we will get like this, and if it is a unipolar polar RZ, so pattern we will get like this. Okay, so remember, if RZ is there, so main lobe is starting from 0 level. Okay, I hope it is clear. So this is time domain and frequency domain analysis of the line codes. This is time domain and frequency domain analysis of the line codes. I hope it is clear. Let me know. Is it okay? but most of the time in the examination आपको time domain में ही आएगा question, means draw the line code formats for a given data format, for the given data format. Such type of question would be there. Such type of question would be there. Okay, so this is all about the time domain and frequency domain analysis of the line codes. So in the next lecture we will discuss about the scrambling. Okay, scrambling is means you might have heard about this word scrambler. Means how do you secure our binary information. Means, for example, let me explain here in short. Scrambling means what? For example, if you have this data, for example, if you have this data 10101, okay, so if you want to secure this data, means if you want to transmit this data securely, so we will use the scramblers. We will use the scrambler. There is a circuit. Scrambler is a circuit. Okay, and this sequence, bit sequence, we will change as a different bit sequence. Like for example, 00101. So how many bits are there? 5 bits. So we will get the 5 bits, but the sequence would be different. So how do you provide the security? Even though we are changing this, the representation of 1 and zeros, that means we are not changing the information here. Just we are providing the security. They are providing the security. Okay, means we are adding some noise level there. But that noise we are using for the security purpose. So such type of problems we will solve in the next session. Okay. If you have any doubt, then you can ask. Is it okay? Okay, fine. So up to this topic, I will upload one question on Google Classroom in tomorrow's offline lecture. So try to solve that numerical. Okay. Okay. Till then, goodbye. Take care.